For generations, humanity has looked into the darkness above and believed that, little by little, we were beginning to understand the universe. We developed equations to describe gravity. We measured the expansion of space. We built increasingly powerful observatories and used them to look deeper into cosmic history than ever before. Then the James Webb Space Telescope arrived. Its mission was not to destroy everything we knew about the cosmos. Webb was designed to test our understanding by observing some of the earliest galaxies, ancient stars, distant planets, and objects whose light has traveled across billions of years. And almost immediately, the telescope began showing astronomers something unexpected. Some of the earliest galaxies observed by Webb appear surprisingly bright, massive, and chemically developed for their age. Instead of seeing only primitive collections of stars, researchers found systems that had already undergone significant growth. This does not mean the universe has broken its laws. It means our understanding of how quickly certain cosmic structures can develop may need refinement. One of the most important examples comes from observations of distant galaxy clusters such as Abell 2744. Because massive foreground clusters bend and magnify light through gravitational lensing, Webb can use these natural cosmic lenses to examine galaxies that would otherwise be extremely difficult to detect. What appeared in those observations was remarkable. Tiny galaxies from the distant past began emerging from the darkness. Some were faint and irregular, exactly as astronomers expected. But others showed surprisingly strong activity and substantial stellar populations. The deeper Webb looks, the more complicated this picture becomes. Astronomers are discovering that the early universe was not simply a smooth ocean of hydrogen slowly producing the first galaxies. It was already developing structure through gravity, gas collapse, star formation, mergers, and the growth of enormous dark matter halos. That raises an important question. How quickly can a galaxy actually become mature? For decades, scientists developed increasingly sophisticated computer simulations to answer that question. These models reproduce many features of the modern universe extremely well. But simulations are only as good as the assumptions behind them. When new observations reveal objects that appear more developed than expected, researchers do not immediately throw the entire model away. Instead, they investigate what could have caused the difference. Perhaps early galaxies converted gas into stars more efficiently. Perhaps galaxies experienced periods of extremely intense star formation. Perhaps mergers happened more frequently. Or perhaps the properties of early galaxies were simply different from those found in the modern universe. Each possibility provides another piece of the puzzle. Webb has also transformed our understanding of enormous structures. Across hundreds of millions of light years, galaxies are connected through the cosmic web, a gigantic network formed by dark matter and ordinary matter. Filaments intersect with dense clusters while enormous voids occupy the spaces between them. From a distance, these structures can appear almost artificial. Long chains of galaxies stretch across space like enormous threads. Dense regions resemble intersections in a cosmic highway system. But there is no evidence that these formations were engineered. Gravity is capable of producing extraordinary order from tiny differences in the early distribution of matter. Over immense periods of time, slightly denser regions attract more material. Dark matter gathers first, creating gravitational wells. Gas falls into those regions, stars ignite, galaxies grow, and eventually groups of galaxies assemble into larger structures. The result is the cosmic architecture we see today. Yet Webb is giving scientists something previous observatories could provide only imperfectly: the ability to observe this process much closer to its beginning. We are not simply studying today's universe. We are looking backward. Every distant galaxy is a time capsule. Its light began traveling toward Earth when our planet, our civilization, and even the modern structure of the Milky Way were radically different. And this is where Webb becomes truly fascinating. It allows scientists to compare the universe at different stages of development and determine whether the transition from simple early structures to mature galaxies happened exactly as current models predict. Sometimes the answer appears to be yes. Sometimes the observations raise new questions. And those questions may be more valuable than any dramatic claim of a discovery that breaks physics, because science advances when observations force us to investigate. The James Webb Space Telescope has not proven that the laws of physics are wrong. Instead, it has revealed that the universe may have been more active, more complex, and more efficient at building structure than earlier observations allowed us to appreciate. And that is only the beginning. Because the deeper Webb looks, the farther back in cosmic history we can see. But the mystery becomes even more interesting when astronomers move beyond the question of galaxies and begin examining the signals hidden inside the light itself. A telescope image is only the beginning. Every photon collected by Webb contains information about the object that produced or emitted it. By separating that light into different wavelengths, scientists can study chemical elements, temperatures, star formation, dust, and other physical properties. This technique is called spectroscopy, and it is one of the most powerful tools in modern astronomy. It allows researchers to ask questions that an ordinary photograph cannot answer. What is a distant galaxy made of? How quickly are its stars forming? How much dust surrounds it? Does its light contain signatures of oxygen, carbon, methane, or other molecules? And perhaps most importantly, how old was the universe when that light began its journey toward us? These measurements have produced some of Webb's most exciting results. In certain extremely distant galaxies, scientists have found evidence that stars formed rapidly and that chemical enrichment occurred earlier than some older models predicted. Again, this does not automatically mean something impossible happened. Astronomers are examining whether early stars could have lived and died faster than expected, enriching their surroundings with heavier elements. They are also studying whether bursts of star formation were much more powerful during the universe's earliest periods. Another possibility is that some of the objects identified by Webb are unusual members of the early galaxy population rather than representative examples of the entire universe. This distinction matters. Finding an extreme object does not necessarily mean the entire universe behaved that way. It simply means nature is capable of producing that object. More observations are required to determine how common such systems actually were. The same caution applies to unusual astronomical signals. Space is filled with powerful phenomena capable of producing strange patterns of light. Pulsars rotate at extraordinary speeds. Black holes can consume matter and generate enormous energy. Supernova explosions can briefly outshine entire galaxies. Magnetars can release tremendous bursts of radiation. Even seemingly regular signals can sometimes have natural explanations that are not immediately obvious. That is why astronomers do not label an unexplained signal as extraterrestrial simply because its origin is uncertain. An unexplained observation is a question, not an answer. This principle is especially important when discussing the possibility of intelligent life. Webb is capable of studying atmospheres around some distant exoplanets. Scientists can search for chemical signatures that might reveal atmospheric processes, including combinations of molecules that could potentially be interesting in the context of habitability. But detecting one molecule would not automatically prove life exists. The chemistry of an atmosphere is complicated. Stars can alter planetary atmospheres. Geological activity can create gases. Radiation can trigger chemical reactions. To identify a genuinely convincing biosignature, Researchers would need multiple lines of evidence and careful elimination of non-biological explanations. That is what makes the current era so exciting. For the first time, humanity possesses instruments capable of examining distant worlds in ways that were previously impossible. And Webb is only one part of this larger scientific effort. Future observatories will provide larger samples, improved measurements, and more detailed observations. As the number of distant galaxies and exoplanets increases, astronomers can begin separating unusual exceptions from genuine cosmic patterns. That distinction could fundamentally improve our understanding of the universe.